Hi all, I'm Marco Gaido. I'm a PhD student at Fondazione Bruno Kessler and University of Trento in Italy. And this is our work beyond voice activity detection, hybrid audio segmentation for direct speech translation that has been done with Matteo Negri, Mauro Cettolo, and Marco Turchi. First of all, let me give an overview of our task. The task we have in mind is speech-to-text translation. So in the input, we have audio recordings, audio utterances, and then we have a speech translation model, which generates the textual translation into a different language. In this case, we have an input utterance whose content is in English, and the output translation is in Italian. Speech translation models are trained on corpora which are made of utterances that are segmented into well-formed sentences. So these models are basically given utterance translation pairs which are complete and well-formed sentences. This is possible because in this corpora we align the transcript with the audio, and then we align the translation with the transcript, and then the sentences are split at the sentence level using strong punctuation markings. So this is not possible actually to be done at inference time, because at inference time we don't have the transcript. So this pipeline is nice and works well, but yeah, at inference time it's not available. So at inference time, what happens is that in real use cases, the audio comes as an unsegmented stream. And first of all, so we need to segment, as models can process only finite segments of speech. You can't give them an infinite stream of audio. So first of all, we need a method to segment the audio streams into different utterances. And this automatical segmentation usually causes two issues. The first one is that there is a training inference mismatch. So models are trained on utterance which contain well-formed sentences, but at inference time, this audio segmentation, of course, isn't perfect. So what happens is that you have a different distribution from the one you have in the training set. And second, there is a context loss. So as in this case, as you can see in this example, when the audio is segmented in the middle of a sentence, the model might miss some context that is crucial to properly translate. And this is also reflected in the scores. Here we can see the score for the same speech translation model on the must-see test set. And in the first case, we use the manual segmentation, which is provided in the ST corpus, and we obtain a 29.1 blue score, while using the voice activity detection to segment the audio. So having an automatic segmentation, we have a considerable drop, and on the same data, we obtain 23.7 blue scores. Currently, there are 3 existing methods that are used to automatically segment the audio. The most widespread one is the voice activity detection, which is based on tools that split on long pauses. So basically, there is a tool that detects whether there is voice or not in a small fraction of time. And if no one is speaking, then the audio split. Another naive method is to split the audio every, I don't know, 10, 20, 30 seconds. I mean, giving a fixed length to each utterance. And then a couple of years ago, a bit less, there was a proposal of another method to segment the audio. But we will see that this method was carried out in a manual way, so it is not really applicable and cannot be applied to input streams because it needs the whole audio before starting splitting. So regarding the voice activity detection, we see that these tools use pauses, speaker pauses as cue for sentence boundaries. So the approximation here is that, okay, when we have a strong punctuation mark, the speaker has a long pause. Of course, this is not always the case, so these tools aren't perfect. And moreover, these tools don't allow to control the segment length, because a speaker may go very fast in a given part of the speech, but then it can be very slow and make pauses in another case. And there are different tools for these. All of them use different configurations. Tuning them is always not easy, and sometimes it's also speaker dependent. And the different configuration can lead to very different results, as we can see in the table on the right. And this also depends on the speaking styles. So throughout this study, we use the segmentation, the segmenter, and the configuration we see in the red rectangles, which were the ones giving the best results for our use cases, as we can see from this table. Then we have the fixed length segmentation, and we can see that for our models, the longer the segments are, and the better the scores. So we can see that the scores increase with the segment length up to 20 seconds, which was the maximum segment length at training time. And then scores starts going down at 22 seconds and so on. Finally, we have the third method, the SR pulse segmentation method, which recursively splits the audio into two parts on the longest pause. So, for instance, we have this long utterance, this long audio. We look for the longest pause in that, then we split the audio into two parts according to that pause, and then we again go ahead and split recursively these two parts, and we go ahead like that until we meet one of the two stopping criteria, which are that there are no more silences, and these silences in the original work were manually detected. And second, whether we stop when the segments are shorter than a threshold. And given that in the previous slide we saw that the optimal segment length for our system is 20 seconds, in our experiments we set this threshold to 20 seconds. This is an hybrid approach that both considers this target segment length, so gives us some assurance on the maximum segment length, and also on the audio content, because it looks for the pauses in it. One of the main issues of this method is that cannot be applied on audio on online audio streams because it requires the whole audio to start splitting, so it cannot be applied in simultaneous scenarios. So we proposed a different solution that is always a hybrid segmentation method, so considers both the segment length and the audio content. And basically what it does is that in a given interval, and in our experimental settings we use 17 and 20 seconds. In a given interval, it looks for the longest pause in this interval and splits on it. So in this case, it looks for the longest pause and then it splits based on it, and it goes ahead like this. We also have another variant of this segmentation in which we split always. I mean, even though we haven't reached the minimum threshold of the 17 seconds, when there is a very long pause, and by very long we mean higher than 550 milliseconds, because this has been shown by previous work to be considered a terminal juncture, which is a break between two different utterances. The benefits of our segmentation are both that we can control the segment length, so we can control the latency. And then also the good thing is that we can apply this to online audio streams, because we don't have to wait for the whole audio to be available to start splitting. We compare our solution to the previous ones, and we can see that in English-German, on two test sets, Massey and Europarl ST, our method outperforms all the others. And in particular, with respect to the commonly used VAD segmentation method, the margin is pretty huge. Moreover, we can see that for English-German, the best version of our method is the one without force splits. On English-Italian, instead, we see that, again, our method is outperforming all the others, but in this case, the method with force splits is the best. So we try to understand why do we see this different behavior. So why in English-Italian we need to split on force splits, while for English-German this harms the overall results. And we see that there are two main kind of errors that speech translation models do when the sentences are not split in a perfect way. And one problem is hallucination. So when we have short utterances, or we have sentences that are broken in the middle, we see that the models hallucinate to generate, trying to generate a grammatically correct sentence. And then we have another phenomenon, which is the one of omission of truncation in presence of long utterances. So the model doesn't know really what to do with some parts of the audio and just omits it, so it ignores it. And in English-German, being an SOV language, differently from English, which has first the subject, then the verb, and finally the object, hallucinations are more frequent because most of the times the models has to put something else to create a grammatical sentence, since the verb is in the very end. So models, in this case, are usually add content to respect grammatical rules, while in English-Italian, being SVO, like English, hallucinations are less frequent, and the omissions are the main problem. So we see that based on the target language, we have two, either one or the other of the problems is the most important one, so the one that has an higher input in the results. And this explains why the method with force splits that creates shorter segments is worse in German, while for Italian it helps because it reduces the number of omissions. So to summarize, we see that we have demonstrated that although it is widely adopted, VAD segmentation is not the best way to go to segment the audio, because it has very low scores, and the quality of ST system is highly influenced by this method of segmenting the audio. And we also noticed that the length of the generated segments is a critical factor for the overall quality of the speech translation model. And in case we have too short segments, models tend to hallucinate and generate content which is not present in the audio. While if they are too long, models tend to truncate, to skip parts of the content. And so some parts are not rendered in the output translation. The importance of either of these two problems depends on the characteristic of the target language with respect to the input one. As we have seen that in German, the hallucination problem is more critical, while in Italian, the truncation problem is more relevant. And so we have proposed two variants that are outperforming all the other methods. One works better in German, the other better in Italian. But by the way, they can close the gap between the optimal manual segmentation compared to the standard voice activity detection tools by up to 54% of the score. Moreover, we see that our method can be used on online audio streams, and this is important, especially for simultaneous speech translation, while the previously state-of-the-art method, the SRPOL1, was not usable in audio streams. So thanks for listening. In case you have any questions, here you can see some context. You also can see our Twitter handle, so you can follow us for further research on speech translation. Thanks.